is what we can call a theoretical cosmologist, because he started his research, his studies in Pisa, in Italy. He has started his research in Munich in string theory. It's only after his PhD that he moved slowly to theoretical cosmology, when he did 2 postdocs in the US, first at Cornell University, and then and after that, we could say that then he worked in theoretical cosmology, and he was appointed faculty in a faculty position in Utrecht for 4 years. And now, since 2018, he's a lecturer in Cambridge in the Department of Applied Mathematics and Theoretical Physics. So after working in string theory, building models for inflation, actually, Enrico worked into non-Gaussianity, into computing what are the levels of non-Gaussianity expected in the various models of inflations. And one could say that Enrico is a specialist of soft theorems. So soft theorems are a scale non-Gaussianity. So non-Gaussianity, roughly speaking, is a coupling between the large and the small scale. And soft theorems are some special properties that you can find when one of these scales is very large. And this, for instance, he has been worked out these soft theorems with Sadraj Azairi, who is a postdoc in IAP. Also, he has turned himself into a specialist of perturbation theory. So the cosmological perturbation theory is the theory that we use to predict the formation of structure. And he has contributed significantly in the effective field theory of large-scale structure. So he has as collaborators, for instance, Fabian Schmidt, that we know on that. And also then, as he moves slowly towards observation, so large-scale structures, he has also worked on spectral distortions. And on this, he has a quite very important paper with Matthias Aldariaga from Princeton, when he was a postdoc there. And then more recently with Jens Schluba, and also with people that we know here in France, with Nabila Ghanim. So one could say that somehow is really a theoretical cosmologist who is bridging the gap between initial conditions, so theory of inflation, he's going to talk about that today, and the consequences on observation, so which are the large-scale structure, or even the imprint on the cosmic microwave background through the spectral distortion. So today, he's going to talk about the Bootstrap method for inflation, which is a timeless method for computing properties of inflation. And so this has this title, A Timeless History of the Universe. So please, Enrico, you have 1 hour, or a bit less, sorry, 50 minutes for your colloquium.
Hey, Cyril, thank you very much for the nice presentation and the opportunity to speak at this event. Can you all see my screen?
Yes, we can.
Very good. And please do let me know if you cannot hear me well, just in case my connection is not great. I'm working from home as many of us. Okay, so the title of my talk is A Timeless History of Time. Of course, it's a tribute to a famous Stephen Hawking's book, A Brief History of Time, and it also alludes to a new way of thinking about the history of the universe, and especially the first fraction of a second. And hopefully by the end, the title will become more clear. Let's see. Okay, very good. Yeah, I just wanted to get started just saying 2 words about my brilliant collaborators, without whom this would not have been possible. One of them is Sadraj Azairi, might be familiar to several of you, because he's now at IAP. And then the other are David Stefanizin, postdoc in our group, and Scott Melville, Hawking Fellow here at Dept, and then my 3 students, Jakob Suppel, Harry Goodhue, and Gordon Manghei Lee, and they've all done a tremendous amount of work for the nice results that are present in the second half of this talk. So I'm going to start, since this is a colloquium, I want to be very broad and really put in front of everything the main motivations why I do cosmology, why I find it a very interesting field of research. And I want to review what the standard approach has been so far in the past maybe 40 years, and then contrast that in the second half of the talk with the remarkable revolution that has taken place in the past couple of years, in which we have learned a lot of very general facts that we didn't know before, and they have given us the opportunity to think about the early universe and inflation from a completely different perspective that I'll call the boostless perspective. So an invitation to cosmology to get started. I like to think of cosmology as a way to put together some of the interesting laws of physics that we have learned about. So this is maybe you've seen it often, is a three-dimensional space where on the axis there are some fundamental constants of nature. The vertical axis is velocity in units of the speed of gravity, or the speed of light, as it is better known. On the other axis, you have the size of actions in units of the Planck constant that tells you how quantum mechanical a given system is. And the last axis describes how general relativistic a system is, whether there is large curvature or large energy densities. And most of the things that we studied here, they really, most of the theories and the fields of research that we have, they lie pretty flat on one of these three surfaces. If we think of, for example, condensed matter is very quantum, but there is definitely no GR, no general relativity, and no relativistic. Classical mechanics is neither quantum nor general relativistic, so lives here near the origin, and so on and so forth. You can think of relativistic effects in astrophysics that don't require general relativity, but are Newtonian, and so on and so forth. You can think of occupying other planes of this cube, thinking about black holes. They're very general relativistic, but as far as we know, perhaps not much quantum mechanics going on, at least as far as the observables that we are currently studying are concerned. And cosmology, I would put it somewhere here. You really need general relativity for the study, let's say, of the cosmic microwave background and large-scale structure, and definitely very relativistic. But the effect of quantum mechanics can be factorized out in the computation of some simple scattering. And most of the problem of cosmological perturbation theory is really classical in nature. So the actions is very large in units of h bar of the Planck constant. So the reason why I mention this is because I think that one field of research that sits comfortably in the bulk of this space, where you have to do quantum mechanics, you have to do special relativity, and you have to do general relativity, is the study of the very early universe. What happened in the first fraction of a second, something that you could call Big Bang cosmology or inflationary cosmology. And what's most exciting is not only we have to study all of this principle of physics at the same time, but we also have observational evidence about what happened. So we can really connect our ideas and beliefs about the laws of physics with observations. So to some extent, the reason why I am most excited about cosmology is because I think of it as a first data set on perturbative quantum gravity. According to the leading paradigm, as I will explain in a second, the distribution of everything in the universe, whether that's galaxies or dark matter, the distribution of light, even the distribution of space-time curvature itself that we measure through galaxy surveys or the cosmic microwave background, they were generated in the first fraction of a second of the Big Bang by quantum processes that require the use of general relativity. So in that sense, we are really studying a new regime of gravity that we haven't tested anywhere else. And at the same time, we are studying very high energy physics, which would not be possible with terrestrial experiments. So that's why I find this field extremely exciting. Just in a couple of slides, what's our standard model? And most of the talk will be about this first part of the history of the universe, in which I'll discuss, we believe, a phase of inflation took place. But really my interest is to make prediction for things like, maybe I should have put the Planck drawing. This is such a nice drawing. I'm really trying to make predictions for the late universe observations that we are making. So that's in the back of my mind, but we really have to understand better what happened in the first fraction of a second. So the main theme of cosmology is that the space-time is expanding. And something remarkable about our universe is that if Einstein gave you the Einstein equation and said, okay, find me some solutions, you say, well, that's pretty hard. There's 10 coupled non-linear partial differential equation. There is no way I can find the solution. You would start with the simplest one. Probably the simplest one would be Minkowski space-time, but the next simplest would be FLRW space-time, which remarkably describes our universe on large scales very well. This is shocking because this is an exact, fully nonlinear solution of general relativity, and it happens to describe our universe. In principle, our universe could have been more complicated on large scales. So this is our starting point. The universe is expanding, homogeneous and isotropic. And the reason why expansion plays such an important role conceptually is because it really changes the way we ask questions. So Emmy Noether here taught us that if you have symmetries, then you have conserved currents. And we think the energy momentum tensor of stuff in the universe is conserved covariantly, in the sense that energy flows from one part of the system to another, and the same for momentum. But there is not a globally defined notion of energy. Because of the expansion of the universe, energy as a charge is not conserved. Technically speaking, the word is that there is no time-like killing vector that we can use to define a conserved energy. And so this changes radically the type of question that we ask in cosmology. You would like to ask questions like, where do we all come from? And the answer to that question can very well be, we come from nothing, because particle number is not conserved, energy is not conserved. So you can start the universe in the empty state and generate everything we observe at late times. And this is completely compatible with the laws of physics, because time translations are broken by the expansion of the universe. So where do we come from? Indeed, we would like, this is the main theme of this talk, understanding how the distribution of everything in the universe is determined. And we have evidence, which I'll review in a second, that this was determined in the first fraction of a second before the hot Big Bang. So it has nothing to do with gravitational collapse of structures or the interactions of photons. This was determined before that. And inflation is the leading candidate. Let's review the evidence. I'm going to show you two pieces of evidence, and I'll show you that combined, they basically lead to our current paradigm. Piece of evidence number one is that if you imagine of looking at the sky and measure, putting your microwave glasses and looking at the temperature in various directions, you could make a map of what is known as the cosmic microwave background. And since these are photons, you can also put on your polarized glasses and make a map also of their polarization. Now you cross-correlate these two maps and you plot it in a spherical harmonic space, some form of Fourier space, and this is the plot. Nice things that they are strongly correlated with each other, and we understand the physics of these oscillations very well. Mostly it's just the oscillations of plasma waves, the fact that plasma contracts and expands regularly, and that explains all of these oscillations. But it does not explain why these oscillations persist on very large scales. The scales here, they were much larger than the causal horizon of the system at the time, and there was no possible physical process to generate this correlation here between temperature and polarization. The existence of this correlation, as opposed to being zero, it's strong, I would say, incontroversial evidence that the perturbations in our universe are primordial in origin. They are generated before the hot Big Bang. This is piece of evidence one. Perturbations are primordial. Piece of evidence two, if you take that map that you did before of the temperature, you can cross-correlate it with itself, and you get this iconic plot of the anisotropy power spectrum of the cosmic microwave background. And you can see that on large scale, it looks like it's pretty much constant. The oscillations, again, we understand very well in terms of plasma oscillations. We also understand the damping. But why is it scale invariant? Since we understand so well this observation, these oscillations, we can evolve the system backward and go back to the initial condition that gave rise to this plot. And those initial conditions within the error bar is that there was the same amount of power on perturbations on all possible scales up to the percent precision. So we have only a 4% deviation from this property, what is known as scale invariant. So our universe on large scales at the beginning had this amazing property that you would not have guessed or expected, that all possible scales had the same amount of power. And we would like to have a simple explanation of why that's the case. And the simplest and most natural explanation is to use the isometries of a space-time to explain it. And the space-time that has precisely this property that all scales are the same is called the Sitter space-time. Is a space dominated by a positive cosmological constant, and it has this scaling symmetry, which you see you can rescale distances as long as you rescale time, and so every distance is the same, which leads to scale invariance that we observe. So just these two pieces of evidence tells us that we need to postulate in the very early universe a primordial phase before the hot Big Bang of the Sitter expansion, or quasi-de Sitter. And that's what we call inflation. I think that the evidence is very strong, and we can think of this as already doing for us something amazing. We are using the universe as a discovery machine. we are discovering that there is new degrees of freedom, new type of matter that must be responsible for this phase of accelerated expansion. And we know that this phase inflation happened at a certain energy scale, it lasted for a certain time, and it sped up at a certain rate. These are all measured quantities. And none of those time scales or energy scales comes from any of the fundamental constants we know about. So there must be new fundamental constants in nature that are not in the standard model that give rise to these energy scales. So we already know that there is much new physics out there to be discovered. So now I'm gonna go a little bit more into the details of how do we describe what happened in the very early universe and make predictions for observations. So the idea is that clearly the system gravity plays an important role. We are talking about the expansion of space-time. But at the same time, we think quantum mechanics plays an important role. So how do we square those two things together? Famously, general relativity and quantum mechanics do not like each other. General relativity is the theory of smooth surfaces called manifolds, while quantum mechanics tells you nothing is smooth. You can never tell me the value of the metric at a point or of its time derivative. It's all fuzzy if you zoom in long enough. And that's true, especially if you ask really deep questions that at the non-perturbative level, that's really hard to find a satisfying description. However, as long as the perturbations that we are talking about are small, as they are in our universe, we have a very satisfactory way of perturbatively quantizing gravity, which is just quantum field theory. Something that we have realized in perhaps the 60s or 70s is that we can treat general relativity just as another quantum field theory, very similar to the one that we use to describe subatomic particles. And in particular, the framework is known as effective field theory. And the framework is pretty simple. Write down the action and quantize it perturbatively. And as long as you ask questions that are below the Planck scale, this theory will always give you precise and well-defined answers for any observable that you will ever compute. So we have a framework to make predictions. And the simplest prediction you can ask is what is the power spectrum, the two-point function? How big are perturbations in our universe? And the calculation is just the same that you do when you learn quantum mechanics 101, when you take the harmonic oscillator and you compute the two-point function. You know that classically you can take a pendulum and keep it there and stop it from moving, that is a vacuum position. But we know quantum mechanically that's impossible. You can never stop a pendulum, otherwise you would determine its position and velocity at the same time, and that's forbidden. The same happens for the components of the metric, which I call Hij and Hii. The components of the metric h mu nu that have a time index are not dynamical, so we don't care about. The off-diagonal one in the space component, these are what we call gravitational waves. And they have a non-trivial two-point function because of the laws of quantum mechanics. Because there is some other matter in the system, there is another degree of freedom, usually something we call the inflaton. And we can think of that as being the diagonal part of the metric in some gauge. The reason why I'm writing this down is because you see that all the fundamental constants that I mentioned at the beginning of the talk do appear in the answer. We have h bar because we are quantizing the metric. We have g Newton because we're using Einstein-Hilbert action, general relativity, and we have the speed of light. And they all need to be used to get the right result. And this here, the power spectrum of curvature perturbations, actually was the second of being predicted. The first one to be predicted were gravitational waves, but we haven't seen them. So far, we only know that gravitational waves make up less than 6% of perturbations in our universe. Finally, before I'm gonna be moving to the second part of the talk, I wanted to mention that you might think that, okay, this stuff happened in the first fraction of a second, but who knows what happened since then? A lot of things happen. It's gonna be very hard to trace back to what happened. But we have, under very general circumstances, and we have very general results, theorems, as well as detailed proof in many set of models, that these perturbations are conserved for most of the history of the universe, as long as they are much larger than the Hubble radius. And so they come to us bringing all that information about the very dense, very high energy early universe And that's it's a fantastic aspect of our universe that allows us to probe high energy physics using observations of very low energy photons, like sub-electron volt photons in the CMB tell us about energy scales that are 10 to the 13 or 10 to the 15 GeV. That's spectacular. And what the field is doing and what the goal of this research field is to try to compute all possible statistical correlation of the initial conditions in the universe. That these are sometimes called cosmological correlators or primordial non-Gaussianities or primordial initial conditions. These are all the same thing. The asking is how the universe was set up to begin with. And we know it was set up in the first fraction of a second. So the rest of the talk will be about how do we compute this? How do we make predictions? What are those predictions? And what can we learn from them? And what has become pretty clear in the past few years is that although we do have a well-defined method of making predictions, which is similar to what I just described, we're using effective field theories and making calculations, that method is perhaps not the most appropriate for the problem that we have. And what I will be proposing is a complete different way of doing calculations and therefore thinking about the very early universe. And perhaps the theme colloquially will be that we will completely get rid of time as a variable, and we will understand the initial condition of the universe per se without referring about the history that made them. And I'll discuss this idea more in detail. So how do we make prediction, I guess in science, but I'm focusing on physics. The standard approach is, I'm gonna call it path one, possibility number one. You start with some fundamental principles. This principle might be things that you have measured very well. For example, the equivalence principle or special relativity. And then you say, well, I want a theory that respects these principles. And then you propose a model. For example, the model could be general relativity, or you can come up with some other scalar tensor theory or something more complicated. And then within that model, you compute all kinds of observables that you want. And for general relativity, we compute very many observables. The formation of structures, the dynamics of astrophysical system, precise corrections to the solar system orbits, and so on and so forth. And very similarly, we do the same in particle physics, just an example. We start from the theory has to be consistent. And since it's a quantum theory, it has to be unitary, and we observe Lorentz invariance to be a very good symmetry of nature. So then we write down the standard model, and from that we compute amplitudes. This is a very reasonable way to proceed when you have a well-established theory. And I think no one will doubt that general relativity and the standard model, they are extremely well established. So it makes very much sense. You write GR and then you take it and compute everything you wanna know about. This is a case in which you have one or two theories and then you make many predictions from them. And this is a very efficient approach. Unfortunately, this is not the situation we are in cosmology, both when we talk about the very early universe and inflation, and when we talk about the late universe, when we describe dark matter and dark energy. We do not have a very well-established theory. We know that if you just write general relativity, that's not enough to describe. We need to assume that there is some form of energy, which is some form of dark matter, some form of dark energy, some field, which is the inflaton that drives inflation. And for all of those situations, we don't have a well-defined models. We have, in fact, way too many models. And when you have too many models, it takes a lot of time to write down all possible models and compute all possible predictions. It's an extremely inefficient process because you don't have like a good target. You don't have your nice, general, well-established theory. And so there might be a different way to proceed, which is what we will do in the rest of the talk, which is let's write the fundamental principle that we have tested well. And let's see if from those we can directly predict the observables that we want to compute. If the observables are simple enough, this might be a very effective way to proceed. And when we talk about probing the very early universe, that's precisely the case. The way we investigate from late time what happens in the early universe is by looking at correlation of cosmological perturbations, whether that's the distribution of galaxies or of dark matter through lensing, or of the temperature and polarization of the cosmic microwave background. The thing we predict are endpoint correlation function, 2-point function, 3-point function, 4-point function. So how are those observables constrained and perhaps completely predicted by fundamental principles? And this is the approach that I want to be taking. Go directly from things we believe in, locality, the fact that we don't want interactions at distance, symmetries, the fact that the universe looks homogeneous and isotropic on large scales, and perturbations, primordial perturbation looks scale invariant, and the fact that theory is consistent. If it is a quantum theory, it has to be unitary. So it can have a consistent probabilistic interpretation, so that probabilities are positive and sum up to 1. And that's what we're going to do. And sometimes this is called the bootstrap approach. We are trying to learn about something without ever computing it, just writing down the most generic solution that is compatible with all the principles we have. And that happens to be extremely successful, as I will show. But it's something that we have learned to do only in the past few years. So we have very many models, but we only test them through correlators. So now we're going to try to spend the next half an hour in finding how all the principles that we know of and we care about tell us what the answer is without doing the calculation. First, I'm going to define more carefully what the cosmological observables are. And I'll talk about the correlators or the wave function of the universe. Then I'll tell you what the principles are, symmetries, unitarity, and locality. And finally, I'll show you how you can already make predictions. Some of these predictions have already been made within models. Some of them, they have never been computed, because this result will encompass all possible models. And we have only studied a few models, not all possible ones. And this prediction can be tested in cosmic microwave background or large-scale structure surveys. So let's start with the observables. What is it that we measure? What is it that we want to predict? So in principle, what we actually measure is pretty complicated, because it depends on how you measure it. It could be the polarization of the CMB. And that can be very hard to compute if you include all the complicated evolution in the late universe. But we can really factorize the problem in what happened in the primordial phase of the universe and what happened later. What happened later is something for which we know the laws of physics, and we can in principle do it. So we will focus here on just what happens in the primordial universe. And the one thing that you want to know is what is the probability distribution of everything in the universe. It is a bit of a grandiose term, but this is something that goes under the name of the wave function of the universe. You could imagine that the whole universe with everything in it is described by a wave function. And if I give you that wave function, you can compute everything you want. It's not a wave function. It's slightly different from the one you studied in quantum mechanics that tells you the probability of a particle or the amplitude of a particle to be here or there. This is going to tell you the amplitude for each one of the fields in the universe, whether it is the temperature of photons or the density of dark matter, to take a value. If I give you this wave function, you can compute every observable you want. Expectation value of anything you want to know is the integral in d phi of psi star of psi, just as we do in quantum mechanics. So the observable that I want to predict is this wave function. Now, there is a remarkable, okay, so, and I should mention for people that are used to think in terms of correlators, maybe because you work in the cosmic microwave background field or in large scale structure, giving you this or giving you all the correlators is the same thing. Once you have this, you can compute the correlators. And you can think of expanding this wave function in the most generic possible way, is the sum of e to the minus a quadratic term, because we know it should be close to Gaussian by observation, plus a cubic term, plus a quartic term, plus a quintic, and so on and so forth. And the coefficient of those higher order terms, you can think of them as being very close cousins of just a correlator. So psi 3 would be the 3-point function, which we call bispectrum. Psi 4 is the 4-point function, which we call trispectrum, and so on and so forth. So the rest of the talk, I'll show you how to compute this coefficient. And once you have them, you can compute all the correlators you want. Now, the other remarkable fact about our universe is that, as far as we can tell, the perturbations in everything are proportional to each other in the very early, in the initial condition. The perturbations in photons, neutrinos, dark matter, curvature space-time itself, they're all proportional to each other. So there is a single function, and this is strong evidence in favor of single field inflation. So in the rest of the talk, we will try to compute the wave function of the universe of a single scalar degree of freedom. And that scalar is what eventually gets converted into temperature anisotropies, dark matter inhomogeneities, neutrino inhomogeneities, and so on and so forth. But this can be also extended to multi-field if you want. But for simplicity of presentation, I'll assume there is only a single scalar degree of freedom that we want to compute. So the wave function, it really tells you everything about the state of a system at some time. So at what time do we want to compute it? Well, we think that the early universe started from some vacuum state at the beginning. It evolved. At some point, inflation ended and connected to the hot Big Bang. What we want to predict, and compute this wave function at the end of inflation, when it can be glued on to the hot Big Bang evolution and determine the initial condition of our universe. So more technically, if we think that the very early universe is described by space-time very close to the Sitter space, its metric must have been close to the FLRW metric, where the scale factor, I haven't written it, is exponential in time. But as long as it accelerated expansion, it doesn't matter. And in this case, we know that the wave function eventually approaches some limit in the future. So we want to compute this in the far future. Technically, we want to compute it at the conformal boundary of quasi-de Sitter space, which just means we take the limit of this thing in the future. And whatever that limit is, that's the initial condition for the rest of the history of the universe. And usually the way we do this calculation is that we start with some initial condition when time goes to minus infinity. We write down a model and we just evolve. We solve Schrödinger equation and we evolve this in time. Unfortunately, this time evolution is not observable because I wasn't there, you weren't there, no one was there during this. The only thing that we get to observe is the final value of this wave function. And so the idea here is, let's try to just get the final value without assuming some unobservable time evolution, which is highly model dependent. And the philosophy, which is perhaps a bit philosophical, but is really, let's focus on the thing that we actually measure rather than the thing that we make up to write the model. And the only thing that we measure is the value of this wave function in the future. So it doesn't depend on time anymore. We only observe its asymptotic value. So you will see that unlike the standard approach in calculating this, none of my formula in the rest of the talk will ever include time. There will be no conformal time, no cosmological time. Time completely disappears. I'm gonna try to, because this result does not depend on time. You've taken the limit of going to the future. And so the idea is that we can completely describe the early universe without really referring to time. On the one hand, you might think, why do you need to do that? I mean, we can just think that there is time evolution. But actually, we know that even inflation is not past eternal. At some point, even the concept of time stops being meaningful in an expanding universe. And at some point in the past, even time didn't make sense. So if we have a way to compute things without talking about time, this can give us a way to ask more complicated questions that we traditionally ask, and perhaps even see some properties that go beyond our low energy intuition of a smooth metric. So let's give you some more details.
Enrico, there is a question. So somebody wants to raise his hand and wants to ask a question. So
yes, please.
Thank you. Before we are going on, in your previous, you present what you call wave function of the universe. And so I think that as it is presented, is a little bit confused. So please, you could clarify me. Here, are you defined the wave function of the matter of the universe, or the wave function, what we call, I mean, from DeWitt, Hawking, Gibbons, the wave function of the universe, including all the metrics and all, I mean, and then the definitions which need to be added to this path integral, I mean, you are defining here. So it's not clear here, I mean.
Yes, yeah.
You are summing on the histories on the matter, on the fields, but not on the histories of the backgrounds and on the metrics and so on.
Yes, this is a perturbative wave function that I'm going to compute, although perhaps the goal is to compute it non-perturbatively, and it does depend on the metric itself, and I will be summing of the possible histories of metric fluctuations. In the simplest possible case, I'll show you result explicitly in this talk, since it's a colloquium, just for the diagonal part of the metric HII, which by a gauge transformation can be just shown to be equivalent to a scalar perturbation. But exactly the same calculation gives me also the wave function as function of the spatial component of Gij, which I think of as the graviton. And so all correlators also of the metric, in particular of gravitational waves, can be computed in exactly the same way. And I'll be happy to give you more details, both at the end of the talk. So this does include the metric, and this computes all metric fluctuations as well. And it's going to be computed perturbatively, of course. But so that's it. Really, it is the wave function of the universe in the sense of the width. So, but I'm not going to try to compute it non-perturbatively, although hopefully in the future this will be possible. Does this address your question?
Yes, and finally, you could also do not have to speak about time and just works in the sense of statistical mechanics and in the sense of Euclidean time. And so,
oh, yeah, there's not
another way. This is another way to don't talk about time, as Hawking, I mean, Hawking introduced it, and it's a very good way. But anyway.
Norma, let's keep that for the discussion, please, and we continue the seminar.
Let's go.
It's not going to be that way. I'm going to really get rid of one dimension. It's not that I rotate it to be imaginary. It's just that dimension disappears completely. But I'll be happy to continue the discussion.
So please go ahead, Enrico.
Different. Very good. So those are the observables. What are the symmetries?
Your microphone is off. Oh. Yes, it seems on now.
Can you hear me now?
Right. Yes, I do.
Okay, sorry. Good. So what are the symmetries of the universe? Well, we know we want it to be homogeneous and isotropic statistically, because that's what we observe on large scales. But we also want to have scale invariance, because that's what we observe on the primordial initial condition, up to a small 4% deviation, which can be included in this analysis, but I will not do so explicitly. Now you might ask, are there other symmetries? The more symmetries, the easier is the calculation. And what we proved recently is some form of Coleman-Mandula theorem for cosmology. We proved that the only additional space-time symmetry that you can add to homogeneity, isotropy, and scale invariant are so-called de Sitter boosts, which are the Sitter analog of Lorentz boost. That is the only symmetry you can add. That's one fact. Fact number two, if you do require that symmetry, then the theory must be free in the slow roll limit of single field inflation. So that's something remarkable. It basically tells you that that's not very interesting. There is nothing to compute in single field inflation. And so we will not do that.
Is this also true when not exact scale invariance is not present, when there is an S different? Can you also have this boost? Thank you.
So this says that you can have, so if you have boosts, then all non-Gaussianity are proportional to slow roll parameters. So they can be non-zero, but they have to be proportional to epsilon or eta, for example. And so it's unlikely that they will ever be relevant in the near future, maybe in 200 years, some future civilization, but they are all slow roll suppressed. To some extent, this tells you something that you kind of knew, that within canonically single field inflation, non-Gaussianity are very small, they are of order epsilon. But this shows it to all orders for all theories. In fact, this proof doesn't even rely on a Lagrangian, it's completely algebraic. So this is only true, so the theory is free when you take the slow roll parameter to 0. If the slow roll parameter are small, then the non-Gaussianity are very small. And so I will not proceed in that direction because I don't think it's very relevant for phenomenology. But it is relevant for more abstract questions about the Sitter holography. But I'm more interested in making prediction for observations, and then I cannot assume the Sitter boosts.
Thanks.
So we have 7 symmetries, 3 translations, 3 rotations, and 3 dilations. I should say that other groups, and in particular, Maldacena, Arcani Ahmed, Bauman, Pimentel, have made some amazing amount of work assuming this is the Sitter boost. And because they have more symmetries, they can set up really powerful relations to bootstrap many of the correlators. I will not do that. I think that's very interesting and theoretically gives you a very strong handle, and it connects to much of the development in conformal field theories. So I think it's really beautiful work. I will not be doing that because if we care more about phenomenology, I think that's harder to connect that with phenomenology because of this theorem. So that tends to compute things that are small, slow roll suppressed. Maybe another way of saying it for the expert in the audience, we know famously primordial non-Gaussianity in single field to be large has to be proportional to 1 over the speed of sound, 1 over CS squared. For that to be large, you need CS to be very different from 1, and that clearly breaks boosts because the sound cone is different from the light cone. So we kind of knew this time. Okay, yeah, let me run. So I'm going to use unitarity and locality to bootstrap these things. And the first idea is unitary time evolution. So in models in which we do have time and we do the time evolution, that evolution needs to make sense. The theory needs to be consistent. And probabilities need to be between 0 and 1. Cannot be negative, cannot be large. And the sum of all possible probability has to be 1. Otherwise, the theory doesn't have the mathematical framework doesn't have a physical interpretation. In quantum mechanics, that is just the statement that the evolution operator is unitary, u dagger equals 1. Colloquially, that's the conservation of probabilities. So perhaps more than 60 years ago, we have learned how that constrains the natural observables of particle physics, namely scattering amplitude. And this goes under the optical theorem and the cutting rules. And this has been a very important tool in computing many of the observables that are relevant for particle colliders. Despite that, in cosmology, we are like half a century late. Until 6 months ago, we did not know what the consequences of unitarity were for a correlator. Until 6 months ago, if I gave you a correlator and I told you I spent 6 months computing this, it's very complicated, this is the result, you had no way to check if I made a mistake, if it actually came from a unitary theory. Fortunately, things have changed, and we now know the answer to that question. And this goes under the name of the Cosmological Optical theorem and the Cosmological Cutting rules. And I'll quickly show you what the final result is without going into the details of the derivation. So we just start from unitarity. Basically, that's where else would you start? U dagger equals 1. Probabilities are conserved. And then we insert that inside correlators. And we demand that this relation is still valid when you put it inside correlators. And the big intuition is that what that tells you is it fixes the analytic structure of the answer. Let's say that you have an n-point correlator. It depends on n vectors that we call k boldface. We are going to separate the norm of those vectors. The norm of k boldface is just k from the angular dependence. And then we prove that for time evolution to be unitary, it needs to be true that if you put a minus in front of the energies and a minus in front of every vector and star, then this combination has to be 0 for every theory. this is quite remarkable. It's good to know. It's something you can check. I give you a correlator. You just do this thing. Is it 0 or not? If it is not, the theory is not unitary. Doesn't matter how you calculated, you made a mistake or you started from a non-unitary theory. Notice the other beautiful thing about this relation is that this relation does not contain time, which makes sense because the observable I'm talking about is the future limit of time. It doesn't have time in it. Yet the fact that it comes from a time evolution is encoded in the spatial correlation. It's quite remarkable, and it's not something that we would have been able to guess before. So in fact, it was very confusing for many years how to find unitarity in an object that doesn't have time. This is the answer. This is the simplest answer when you have a single interaction. Since this particular combination will occur over and over in this business, we have a name for it. We call it discontinuity. So precisely this combination, the wave function plus itself with a star, with minuses in its argument, we call it the discontinuity. It's just a name. There is maybe a deeper reason, but I'll just call it a discontinuity. So more generally, this rules generalizes to all possible diagrams. If you have a more complicated diagram with two interactions, you can imagine of the discontinuity of this is equal to you sum over the all possible cuts of internal lines. There is only one internal line, so only one way to cut it. When you cut it, you put the line to go to the boundary. This becomes two 3-point functions, one and the other, and you take the discontinuity of each. If the theory is unitary, this equation has to hold. What's amazing about this is that this is valid for all diagrams, to all orders, to all loop orders, for any particle of any mass, any spin, around any FLRW that admits a Bunch-Davies initial condition. So it's an astoundingly general result that actually surprisingly we didn't know about. And it's valid for loops as well. And this is very interesting because computing loops is very complicated, but this gives you a way. You write any diagram you want, sum over all possible cuts, the discontinuity of all diagrams has to sum up to 0. So we have a 60-year delay with particle physics, but we're finally trying to catch up. I want to show you a little bit more of how we can use this to actually compute something. So far I'm just giving you the constraints, and you can say, well, it's nice, I could check them, but as long as I didn't make a mistake, that would be true. But actually you can do much more. The other physical idea is that we don't want interactions at distance. So what we recently proved is that requires this other condition to be satisfied. The derivative of these correlators with respect to the energies when all other variables are kept fixed needs to be 0 when that energy is 0. So that the first derivative has to be 0. We call this the manifestly local test. If you give me a theory that violates this, the theory cannot be manifestly local. Extremely simple. Again, this is a relation that doesn't involve time. It never says interactions go from here to here. It only says, give me the final result. If it doesn't obey this, it's out. Notice that these relations start to become pretty powerful. We are putting many constraints on these correlators. So you might hope that the full result is completely fixed by all of these constraints. And that's indeed the case. And I'm going to show you very quickly how you can compute a very general result, which is the bispectrum. Now, as a previous question, I could do this for gravitons, compute 3-point function, 4-point function of gravitons. I compute it for scalar. I compute it for multi-field inflations. But okay, here I have little time. I'm going to show you the simplest example in which there is a single scalar. But this generalizes. First of all, we want to write the most generic ansatz, which is compatible with all the symmetries. It should be, for the 3-point function, it should be homogeneous and isotropic, so can only depend on the length of the 3 momenta, because they have to sum up to close up into a triangle. And those lengths are K1, K2, K3. Since the fields are the same, it has to be both symmetric, so it should be invariant under all possible permutations. And there is a theorem in mathematics that tells me that all possible symmetric polynomials can be written in terms of these 3 variables, which are just symmetric combinations of K1, K2, K3. Finally, we know that we are at 3 level in the system, which means this is a rational function. We know it's scale invariant, so the scaling of the polynomial is completely determined. And the choice of a Bunch-Davies vacuum in the far past completely fixes the denominator to be K total to some power P, where P is the number of derivatives in your theory. So now the problem of computing this has been reduced to just computing a bunch of coefficients in a polynomial, which is much, much simpler than doing the full calculation. The most generic function of this to any ordering derivatives is just given by a polynomial here with free coefficients. And those free coefficients are completely fixed by manifest locality. You have to demand that the derivative of this is 0, and that gives you a bunch of constraints on this numerical coefficient. In Mathematica, it's one line to compute it, even numerical, even by hand, you can do this calculation. It's purely algebraic. There is no time integrals, there is nothing fancy going on. And just this function, you take derivative and solve it. And what's beautiful about this is that this captures all possible bispectra in a very generic class of theories known as the effective field theory of inflation, which encompasses all single field models within certain set of assumptions. And this calculation gives you the result to all ordering derivatives. While if you did the calculation explicitly, well, you would compute 2 derivatives, 3 derivatives, but it would get pretty messy. And just to give you a feeling for what the result is, since I'm running out of time, if you do this simple exercise at 0th ordering derivative, you get this line here. When p is 0, you have to interpret this k to the p as being a log. And this predicts exactly the result. This here, this part here is what is known as local non-Gaussianity. And that's something that is vigorously studied in large-scale structure surveys in the CMB as well. And for example, in the scale-dependent bias of galaxies. The second line, there is no solution. Third line, at 2 derivative, this is the only solution. And indeed, if you go through the past 20 years of literature, you will find this formula corresponds to dBi inflation. At 3 derivatives, there are 2 solutions with 2 free parameters. And if you go through the literature, you'll find that these are what's known as equilateral and orthogonal non-Gaussianity that have been vigorously pursued and constrained by Daplumet first and Planck later, and they have some constraint. And here I plotted them. But their shape is completely fixed by this argument. And notice I didn't have to do any time integrals, any informalism. So it's an extremely powerful approach. Finally, there are infinitely many extensions that I don't have the time to discuss here. Something similar can be done for non-Gaussianities, and I could show you in just 2 pages how to compute the graviton 3-point function. So if you want to ask me, I can show you that. It's much faster than the traditional calculation. It's completely transparent. You saw where I put the principles and how I got out the result. So you can tell me if you want to change the principles, you can change the result. Otherwise, you can. And can be extended to fields of any spin. It actually doesn't work only for a contact diagram, but also for exchange diagrams. And I don't have much time to discuss this, but this is perhaps one of the most exciting things that we have been able to show, that there are recursion relations, that if you give me the 3-point function that we have computed so far, then I can take some derivatives of it, and using Cauchy's integral theorem, I can glue 2 3-point functions together to make a 4-point function. And there is a formula in which every term in the formula is completely fixed by these equations. And this is just the result of doing Cauchy's integral theorem. And so this point function, in fact, with any number of external leg on the left and on the right, is completely fixed by the calculation we did previously. And this is the explicit result. And this has been extremely powerful in the amplitude community. And now we finally can do this for correlators as well. Notice I never use the Sitter isometries. Finally, you can do this even for loops. So you can go fully quantum. You might know that loops has been a very hard and perhaps controversial topic of discussion in the inflationary literature, with various results being found and heated debate being had. Here we can compute loops just from 3-level calculations using this cutting rules. For example, you take this 1 loop correction. If you put only 1 leg on each side, this is the power spectrum, something that we measure in the sky. You would like to know if there is a 1 loop correction. And then this optical theorem or cutting rules tells you should sum over all possible cuts, and you get only 3-level stuff, right? Because you're cutting the loop. This 3-level stuff is something you can compute. It's just 3-level. And this completely fixes the discontinuity of this 1 loop correction. And we show that indeed it gives the right result even for, for the effective field theory of inflation, the most generic single field model. And we computed results that had never been computed with other methods. This is the first time that this full result is presented because the calculation was too complicated. Well, this method is straightforward because it's 3-level. So this is another beautiful result. Okay, I'm aware that it's very late, so I'll come to a summary. The first part, I just wanted to say that it is a unique opportunity that cosmological observation allow us to say something about the first fraction of a second, to discover new particles and probe the perturbative regime of quantum gravity. We've made tremendous progress in the past couple of years in understanding how fundamental principles fix these observables in a way that we hadn't in the previous 40 years, because we were building a lot of models to see what was possible. But now we are understanding it from a more fundamental point of view. We understand unitarity through the cosmological optical theorem and locality through this manifestly local test. And now we can turn the table around and say, instead of checking these properties in a given model, we can take these properties to compute the solution. And we have shown how to do that for, well, for many different cases. And so the Bootstrap approach seems to be very successful. I'll stop there. Thank you very much for listening.